so that I can manually unplug the little metal tab and then squeeze it back in.
I seem like a multi-tool guy. Like I'm spraying.
Well, I mean, I don't have a multi-tool, but I do have a set of kind of screwdriver.
Yeah, they go, those go
Co jsem tam vůbec napsal? Ale nic prostě. To by mi nevzali. Něco dostatečně obecného, tam rozchovat skvěl.
Hey guys, so please come, take a seat. We're about to start. Thank you very much. Okay, so please quiet. So in the next 45 minutes, Jan Šapanek is going to present you a bit about persistent storage in OpenShift. So in this talk, you will learn how OpenShift brings persistent storage into the world of stateless containers. So Jan, it's your turn. By the way, one note, please don't forget to rate the talk. So 5 stars for Jan.
Yeah, I will check it. So thanks for coming. Welcome to my talk. As Jarda told, I will be talking about OpenShift storage. I am software engineer working at Red Hat. I work on Kubernetes actually. I don't work on OpenShift, but OpenShift is just Kubernetes when it comes to storage. I will show you how to use existing storage inside OpenShift. If you have some legacy application and you are now trying to containerize it and run it in OpenShift so it can access the old data. I will show you how you can create and delete storage dynamically in OpenShift. And in the end, I will try to show you, if time permits, how to build a scalable application using persistent storage. That's the goal of this presentation. So before I start, I will very briefly talk about OpenShift. OpenShift is container orchestration framework. It runs containers on a cluster. And it doesn't run containers only, like single entities. The smallest entity it runs is pod. Pod is collection of containers. Typically, it's just one container, but you can have as many containers in a pod as you want. For purpose of this talk, pod and container you can take as a synonyms. I won't talk about many containers in the pod. It's the same, like one for me from the storage point of view. And as I've said, OpenShift is Kubernetes plus additional features. And when it comes to storage, we don't have any additional features for OpenShift. Everything I talk about will work in OpenShift. It will work in Kubernetes. And I will talk about future OpenShift, what you will see in the next release, 1.5. And that means I can show you Kubernetes 1.5, which has been already released. So talking about future OpenShift, I will talk about current Kubernetes. One difference between OpenShift and Kubernetes is that in OpenShift we take security seriously, and well, more seriously. And there is a distinction between administrator of OpenShift cluster and user of the cluster. User of the cluster in this case is somebody who deploys applications on OpenShift. Typically, it's a developer or some DevOps guys. This user in an OpenShift sense is administrator of application inside OpenShift. So, As I have said, OpenShift and Kubernetes, they run containers. The containers are ephemeral. They are started, deleted, and every change that the container does, everything what it writes, is lost when the container dies. So to bring some persistence into these containers, we mount stuff into the containers, and we can mount many things. We can mount shared file system like NFS, Gluster, Ceph. We can mount block device, remote block devices like iSCSI, Fiber Channel, Ceph, Quobyte, Flocker, and Photon. If you don't know what it is, these are Quobyte and Flocker are new startups in Silicon Valley. Photon is something vSphere invented. And we can mount storage from cloud. If you run your OpenShift on Amazon, you can use AWS Elastic Block Storage, I think it's called, EBS. If you run on Google Cloud Engine, Google Compute Engine, you can mount persistent disk, you can mount native OpenStack storage, native Azure storage, native vSphere storage, and so on. We have also some special file systems, which I won't cover in this talk because they are not persistent. In Kubernetes or in OpenShift, you can define a secrets, which is just key value map, where you are supposed to put credentials that the application you are deploying on OpenShift needs to connect somewhere, for example, to the database. So you create a special secret object inside Kubernetes, and Kubernetes can mount or create a file system inside the containers which will hold the credentials for you. So your applications can find it and can see the username and password and can connect to the database. And last but not least, we have a flex volume, which is like omnipotent thing. All these plugins on the slide, they are hard-coded inside OpenShift. They are not plugins, actually. You cannot dynamically load and unload them. They are hard-coded in Kubernetes and OpenShift. So if you have a new storage and you want to talk to it using OpenShift, you have to write the plugin. And the flex volume is for you if you don't want to write it. You just distribute shell scripts which can mount the storage and unmount it. And Kubernetes will call the scripts when it needs to mount the storage to your containers or unmount it. And this will get extended soon, I hope. And most of the stuff here will move from OpenShift code, and it will move into Flex, hopefully, because this is hard to maintain. There are so many plugins to maintain, and everybody wants his own storage there, and it's really pain to maintain it. So, as I have said, pod, for you who don't know OpenShift, a container, is ephemeral. And if you want to use some storage outside of OpenShift, you can directly type the coordinates of the storage. If it is NFS share, you type the server address and the share name into the pod, directly into the pod. You can, if you want. I have an example, I think. Yeah. So this is a pod definition. In OpenShift, everything is defined by YAML files. And this pod runs one container. It runs a busybox. Inside the busybox, it runs some busy loop that writes something to /mnt/demo/demo.txt. And it mounts an FS server from this address, this share, and it mounts it into this directory. So if I now cross your fingers because if I oops I have this pod running and it writes I can see that OpenShift mounted this magic share into somewhere inside OpenShift. Well, as I've said, I'm not running OpenShift, I'm running current Kubernetes to show you future OpenShift. So it mounted somewhere into Kubernetes internal tree, and if I look on the NFS server, I can see it's writing something. So this way, if the pod dies and it is restarted on a different node, it gets the same share mounted, and it can continue writing the data to the same file. So that's how we ensure persistence in Kubernetes and OpenShift. But for application developers and OpenShift users, they need to know where the storage is. They need to know the share address, the NFS server address, the share name, and this is not portable. If I have this application in my test environment, I have one share with data, and if I move it to production, then I have different share with the data. And we don't want users to know details about the storage. We want to hide the storage. So later I will show you how we get rid of these magic IP addresses and share names in pod definitions and move them somewhere else where it can be managed by administrator, and the user doesn't need to know anything about the storage at all. So why am I using this direct connection to the storage? It's quite useful if you know what you want. If the user really knows, hey, this is the storage I will ever use, I will never use anything else, then this is useful. This is useful for debugging purposes. You don't need to create any other objects. You can connect to the storage directly. And this method, where you put storage details inside the pod definition, this is useful for the non-persistent storage, like the secrets, like the config map. And I will show you empty directory, which is kind of special storage. It's not persistent. When the pod dies, the empty directory dies. And what does it do? It provides just a storage for your data outside of the container. So you don't pollute your container with files because you don't know how big it can be. You can put typically some caches there. And how does it do? How does it work? This is the same pod. Up to this line, it's the same like before. You just won't mount NFS share into the pod. You will mount empty directory and memory. That means you will get really fast TempFS-based storage inside your pod. So even unprivileged and privileged pod can use TempFS for some fast caches. So that's basically the only reason why you should use the storage directly. As I have said, if you really know what you want for debugging purposes, for non-persistent storage, and for caches. So now it becomes interesting. So as I said, we don't want the users to know details about the storage. Before I start talking about the objects we have for persistent storage, I have some analogy in OpenShift. Everybody uses this every time. In OpenShift, if you start the pod is basically a request to compute something. Request for CPU, for some memory, and to run some container inside it. And in OpenShift, we have node objects, which represent some compute resources outside of Kubernetes. And if you submit a pod to OpenShift, there is a scheduler, and it schedules a pod on a node. And something very similar we have in storage. We have request not for CPU and memory, but for storage. And we have a sort of scheduler that finds the storage for you. So let's assume you have some storage outside of Kubernetes, be it NFS shares, iSCSI, Amazon volumes, whatever. The administrator, the OpenShift administrator, creates a persistent volume objects representing the storage outside of Kubernetes. So for each volume or NFS share or anything, it creates one persistent volume object that represents the storage. The user who wants to run the pod, he creates the claim. There's a request for a storage. The user says, I want to store 5 gigabytes of data somewhere. Please, OpenShift, find me a place. And what OpenShift does, it has a sort of scheduler. It finds a volume for you. And finally, the user can run the pod. OpenShift looks at the claim. The claim points to persistent volume. It points to the storage. And the storage is mounted into the pod. And the pod is happily running. So, is this understandable? Any questions about this? Persistent volume represents the storage. Persistent volume claim represents the user's request for storage. And it's bound together. This binding between volume and claim is pretty strong. Nobody else can use the volume while it's bound. So nobody else can steal your data, basically. The volume is bound only to the claim, and the volume is available only through the claim. And here is how it looks. Persistent volume, it's a pointer to the remote data. Again, there is the pointer, the NFS IP address, and the share name. It has also some metadata, for example, capacity, which says how much storage it can hold and how it can be accessed. For example, this read-write many means that this volume can be mounted to several pods. Because this is an NFS, this is a shared file system, you can mount it several times. If you have a block device, it can be typically mounted only once, and it would say read-write once. And on Google, there is a special kind of storage that can be read-only many times. So you can mount it read-only to several machines. I will talk about it later. So the persistent volume represents the storage, can be used only by a single claim, and it's a global object. So if the OpenShift administrator creates the PVs ahead, these PVs can be used by anyone. I will talk later about how to restrict some volumes to some namespaces, but by default they are global, and they are managed by the cluster administrator. Here are some details. Each persistent volume has, in the metadata, it has its own reclaim policy. By default, it is retain, but it can be also delete and recycle. And the reclaim policy tells what happens to the data when the user says that the data are not needed anymore. So the user has a claim, has pods running, writing some data to the volume through the claim. And when the user is done and says, I don't need the data anymore, then the reclaim policy is executed. And retain means that the volume is there forever, and it cannot be bound to a different user, because there can be credit card details, usernames, password on the volume. We don't know. OpenShift doesn't know. So we won't allow anybody to read the data. But administrator can get to the data if the user changes his mind, says, oops, I deleted something accidentally, please give me back the data. Then the retain policy. With the retain policy, you can actually get the data back. With delete or recycle policy, you won't get the data back. If the user says, I don't need the data anymore, we either delete the volume completely, or we delete all the data on the volume and make the volume available back to any user. So I have an example how it works. So user has asked for some data, for some storage using a claim, PVC, and runs a pod. A user can run as many pods as he wants with the claim. The data is still available when the pod dies. He can start the pod again or different pod and still has access to the data. The way how user says that he doesn't need the data is that he deletes the claim. When you delete the claim as a user, you say you don't need the data. And if the reclaim policy is delete, then OpenShift will delete the volume and will delete the persistent volume in OpenShift. And you can't get the data anymore. So please don't delete your claims unless you really know what you are doing. And how does the claim look like? As I have said, it's a request for storage, where user says, I want to store, in this case, 1 megabyte of data somewhere. Please find me storage. You can specify, I will show later how you can narrow the volumes, the set of volumes you want to claim. And important about the claim is that it is namespaced. In OpenShift, we have objects and pods and namespaces, so different teams or different users don't clash with each other. So if a user creates a claim and gets a volume eventually, then the claim can be used only from the namespace. You cannot share one claim among namespaces. The claim can be used by multiple pods, as I showed you. And yeah, beware, deleting claims is dangerous. So, some demo. I have.
Sorry, by multiple pods you mean, but not simultaneously?
It depends on the persistent volume. If it is shared file system, you can use it from different pods at the same time. If it is block device, it depends on the file system typically, and typically you don't.
And if we set as access mode read write only once, is there something that checks that?
The question is if the access mode is read only once, read write once, there is nothing that checks that. Typically, the second mount fails, and the user gets some error message.
And the retention policy is managed by the pods?
The retention policy is managed by the guy who creates the volumes, persistent volume. That means administrator. But we ensure if you delete the claim, you don't get your data anymore. So it's either deleted, recycled, or it's retained. The data exists, but nobody can access it through OpenShift unless administrator do something. Admin does something. So I have a volume. Again, my favorite NFS share. And cube, cattle, create. I create it. I have a claim. Where is it? Which asks OpenShift for 1 megabyte of storage. And get PVC. Come on. If I look, I created a PV, I created PVC, and they get bound together immediately. So my claim says it is bound. It is bound to this volume. I have 2 megabytes. I asked for 1 megabyte, but I got 2 because that's the smallest volume we have. I can access it from multiple pods, and I can run a pod. Oops, now I have two pods that use my NFS share. Oops, so what happens? And they are happy. Both are writing to the same file. I should delete one. I will delete both actually. And if I look at the persistent volume details, it has a status bound. That means that it's bound to my claim. And where is the retain policy? Here, reclaim policy. Reclaim policy is retain. So what happens if I delete my claim that is bound to this volume? It says that the volume is released. Now, nobody can bind to this volume anymore. So if I create the claim again, the old claim, that the claim is pending. That means there is no volume for you, sorry. And it will be pending forever until somebody creates some volume that can bind to it. So nobody can access this released volume. So I will delete it. And let's continue. Question?
Quick question. Is the size of the volume somehow enforced of the claim? Or you said it's like 2 megabytes for the persistent volume, and let's say that the NFS share has like a gigabyte of the file system underneath it.
The question is if the size of the volume is enforced, and it depends on the volume. If it is NFS share, it's not enforced actually. If it is Amazon volume, this basically block device, it's always restricted to the size of the block device. If it is shared file system, it's usually not. So it's just a number that nobody enforces. So now now the administrator has created a lot of persistent volumes, and if you want to, and now what if the user wants some specific volume? In the persistent volume claim, the user can say what kind of storage he wants, and he can request something that can be shared among pods. That means he wants read-write many. Access mode. This is for NFS, clusters, FFS, and this kind of shared file system. Or the user can require something that can be read and written only in one pod. That's the read-to-write one. In Google, there is one special kind of storage. You can mount read-only to many pods, and it's block device, actually. It's not a shared file system. So this way, the user who submits a claim can say what he wants. I want a shared file system. I want a block device, basically. So each persistent volume lists in its metadata how it can be used. For example, in NFS share, you can use it from single pod, and you can use it from multiple pods. And in the claim, the user says what he wants. I want something that can be shared. And OpenShift then compares these requirements and the existing volumes and chooses something that fits the requirements and is small enough, is as small as possible. We are binding the smallest volumes first. Then you can require a storage class. A storage class is a quite new concept in OpenShift, and storage class puts together volumes with the same characteristics like speed or redundancy or price or anything. This is defined by the cluster administrator, what the classes he wants to so this way, the administrator says that the persistent volume belongs to storage class fast. The names are completely arbitrary. Administrator can define as many classes he wants. And to put a volume into a storage class, he just says, he just puts this magic annotation into the claim, into the PV, sorry. And when the user wants storage of some special class, he puts a magic annotation into the claim, and Kubernetes matches this and finds the best PV with storage class fast in this case. Then we have something very similar to storage classes, which is labels. In Kubernetes and OpenShift, we use labels for anything. Every object can have labels. It can have as many labels as you want, which is different to storage class. Storage class can be only one in a PV. And the user then can request a volume with specific labels. For example, I have a volume that has labels shape square and color green, and the user wants some persistent volume with shape square, and this will match. If the user will want shape, I don't know, triangle, it won't match. So, when to use classes and selectors? These are kind of the same concept. You label PV with labels, or you tag it with storage class. This is the same, basically. But there is one difference. If you don't say anything in the claim, if you omit the selector, then you say, I want a persistent volume with any labels. Give me something. I don't care what it is. On the other hand, if you have a claim with no class requirements, then the user says, give me the default storage class. That's the difference. This way, you can restrict some volumes to certain namespaces using quota. Because, do I have a slide about quota? Yeah, I have. So I will say about quota soon. So that's the difference between classes and selectors. If you don't specify any selector, you get anything. If you don't put any class into the PVC, you will get the default storage class. And how can be used with quota? I have an example, I hope. Where am I? It's 4. Yep. So I will create a quota that's just, it says that quota is per namespace. So this namespace can now have 500 gigabytes of volumes with default storage class, the class named default, and can have 0 gigabytes of storage class goat. So if I label my volumes accordingly, I can say that this expensive SSD RAID array is goat, and I can make it available only to finance department because they are paying goat. And default, I don't know, rotating hard drives, I will give only to IT because, I don't know, they only dig bitcoins and they don't need storage. So the quota and storage class is the way how to do it. Okay, do you understand that at least a bit? Okay, I see some notes.
But you apply the quota to import or?
It's per namespace. Quota is per namespace. So I can create as many claims as I want. I can create as many pods as I want. but the claims cannot be, I cannot claim more than half a terabyte. After that, if I, do I have a claim? I have a claim that requires a gold storage class, and if I create the claim, Kubernetes OpenShift immediately says that sorry, that extends your quota, so I cannot create. And that's just a claim that wants 10 gigabytes of gold. And this namespace cannot claim anything in gold at all. With labels and selectors, you cannot do this. If you label your storage like fast and slow, there is no way how to restrict these labels. Oops, only 10 minutes left. So I'll speed up. You cannot restrict it using labels and spell selectors. So this, what I've thought about is, I call it static provisioning. Somebody from OpenShift administrators creates the volumes ahead, creates the persistent volumes inside Kubernetes, and user can claim it. So this way, the user doesn't need to know anything about IP addresses of your NFS servers, share names, volume IDs, anything. He just creates a claim. I want 5 gigabytes of something, give me that. But who is in trouble as the administrator? He doesn't know how many PVs should I create in advance. Like, how big should they be? And for that, we invented dynamic provisioning. In dynamic provisioning, we envision a situation when there is nothing created outside of Kubernetes, no persistent volume exists, and user creates a claim. I want 5 gigabytes of something. OpenShift creates the storage by itself, creates the volume, binds everything together, and user can happily run the pod. So for that, we need a storage class object. Storage class, as I've said, that it puts together persistent volumes with the same characteristics. And it's a new object in OpenShift 1.4. And it contains parameters for dynamic provisioning. That's the important enhancement now. So the storage class, it's again defined by the administrator. It has some arbitrary name. The admin can define as many storage classes he wants with different names. What's important, it has the name of the provisioner and parameters for the provisioner. So that means, in this case, it will provision Amazon volume with the best IOPS you can get there. So it's really fast. And in OpenShift 1.5, we will allow a default storage class to be defined. That means if a user submits a claim that says just give me 5 gigabytes of something, I don't care what it is, he will get the default one. And how he does it? The default storage class has this magic annotation. It will move somewhere here into the parameters, but now it's annotation. In OpenShift 1.4, we have provisioners for Amazon, Google, OpenStack, Cinder. In 1.5, we will get more. And what's important, we have external dynamic provisioners. That means that somebody can write a piece of software, run it somewhere. It can run as a pod inside OpenShift. It can run outside of your OpenShift infrastructure if you want. And it provisions the storage outside of OpenShift. So you don't need to write a plugin inside OpenShift, which is, it's not hard, but it's hard to get the code in and pass the reviews and such. You can write something by your own. And we have NFS provisioner. Where is my NFS 05? We have created NFS provisioner which runs as a pod, and it creates an FS share inside the pod. That means if somebody kills the pod, the data is gone. So it's not for production use, definitely not, but it's good for testing and development. So on your local machine, you can have something that's dynamically provisioned. I see some question.
Yeah, what is the relationship with like the open service broker API project? Like, because it almost seems like what you're building is a broker.
What's this relation to open service broker?
Yeah, like the open service broker API project.
I don't know anything about that, so
Yeah.
probably none. I have a storage class, which is very simple. It defines a storage class named default, which is default, and the provisioner is it's a string. It's nothing magic in that, and this string is provisioned by the pod I'm running. I hope it's not running because of stupid network. So I need a pod with this. No, it's here. It should work. But from some reason, oops, no, network is busted.
Okay.
Sorry, I won't show that.
You have wire there, so we can try wire.
No time for wires.
So a question. Any questions on handling user permissions for persistent volumes? Like in case we're running a container with a non-root under a non-root user, how do I make sure that that user has permissions to write to the persistent volume?
The question is how user permission works if if the containers run as basically random users. And the answer is you can, in the pod definition, you can specify supplementary groups and FS group parameters, and Kubernetes OpenShift will then run the pod with these groups with a random UID, but the groups will be there. So if you make the storage available to the groups, then it's kind of way how it should work. So it's not bound to user ID, it's bound to groups. So in this dynamic provisioning, if it worked, you would see that I have an FS share, but I don't. The user doesn't need to know anything about storage if he doesn't want to. Of course, the user can use selectors, labels, storage classes, and whatever. But if the user says, I want 5 GB of data, that's fine. Administrator just configures the storage classes to provision something, and everything magically happens. So this is the way we envision for a new application. When you are building a new application, you don't have any legacy data, you should use dynamic provisioning if it is possible.
Tam cedulka na opakování otázek, tady tam. Pak je tam taková látka, takže